So I'll adjust the due dates as needed for this. But right now we're going to go over these recursion puzzles. Once again, this is an assignment where you do get to choose some subset. There's so this one is worth 150 points. So not as big as the, I believe it's 150 points, yeah. Not as big as the linked list, but still a big problem, I would say. And there's going to be 2 chess problems. If you don't know how to play chess, that's fine. I would highly suggest learning just because it's interesting. But we've got 2 chess problems, puzzles, so to speak, which really don't have anything to do with the game of chess itself. More like, here's a chessboard, here's chess pieces, here's how they move, solve a puzzle based on that. The other problem is basically making a Sudoku solver, and I'm going to go through both of those right here. The big thing to understand, though, is that this problem has been a homework problem since my professors were students, okay? The 8 Queens problem is like a classic homework problem, which means, of course, that the answers are on the internet for this, for any language, anywhere, in any format you need. I urge you to show restraint and try solving it yourself. If you cannot solve it yourself or get stuck, speak to me so I can lead you to that answer, rather than you looking up the answer and not benefiting from the problem-solving process, right? This is entirely about exercising and building your muscles. This is a great problem. This is an excellent problem to understand how recursion with backtracking works, okay? Because you have done recursion before, yes? In some way, shape, or form.
Show of hands, how many of you guys mess around with recursion? Probably from that. Okay.
From Fiori's class, right? So, and so this one is just simply a good problem to do. The Knight's Tour is slightly less well known, but well known enough that, again, same thing applies. You could easily look up the answer. The Knight's Tour is more challenging. You will not get any additional credit for solving one versus the other, but I know that there's a number of students who enjoy having the challenge or being able to work on themselves. There is extra credit for this one, though, that is available, and I'll go over that in a second. Sudoku, again, very kind of classic solver. I used to do this one in class. As far as this one is as like an in-class example before I gave it as a homework. In fact, that was the kind of criteria. If I could do it in class in a single session, then I thought it was reasonable to add as a homework. The extra credit problem is Project Euler, problem 96. Project Euler, if you really want to get some programming and math practice in, Project Euler is the way to go. These first kind of problems are really kind of straightforward, but then as we go on, they get more difficult. For instance, lattice paths requires you to kind of use memoization or some other kind of dynamic programming, one of the two, in order to solve it. And then they also are, let's see. And then finally, the other kind of classic dynamic programming, if you are not aware of that, is doing this problem, coin sums. If you are not don't know about dynamic programming, it is worthwhile to know if you are trying to aggressively target an internship. Dynamic programming is extremely powerful. Typically, the best way that I should explain this is that dynamic programming was coined by a math researcher who wanted to basically get funding, and so he called it dynamic programming, even though the technique had very little to do with programming. Simply put, recursion is basically solving a problem from top down going to the base case. Dynamic programming is more like that proof by induction where you start at the base case and then move forward. Competitive Programmer's Handbook. So this is linked to in Discord, by the way. I have a link to this in Discord, the Competitive Programmer's Handbook. I don't know why competitive programming is a thing, but it has a good summary of all sorts of things, including your data structures, complexity classes, as well as an entire thing on dynamic programming and that aforementioned coin problem. Okay. But anyway, Project Euler is just this great resource of stuff. And it does, the other thing I should mention is that it does make you figure out how do I deal with stuff that my programming language might not support, like this one. Work out the first 10 digits of the sum of the following 150-digit numbers. And so in other words, add these together, give me the first 10 digits. Now, Python, you just simply put this in a file and read the file, because Python don't care how big or small integers are. It handles that. On the other hand, these are bigger than ints, which go up to like a maximum 2 billion. And these also go up to longs, which are so big that I don't even bother memorizing how big they are. So you can't store these natively as integers or longs. So how do you do that? And the answer is you have to figure out, is there a class in Java that lets me do numbers that are bigger than really big numbers? And there's the big integer class for that. So it's figuring out, okay, how does my programming language get around these facts? And if it doesn't, how do I build an adder that adds these kind of things? Because you could always make like a long to represent this portion and a long to represent this portion and so on and so forth. And then do the addition manually, like a calculator with carries and adds. Okay. I will talk about, let's see, one last thing before I go into the actual problem. I will go into, the recursion quiz is interesting. There's a question about looking up something called either memoization or tail recursion in there. So those are two kind of advanced techniques, and I'll be happy to talk about memoization in class because it's very valuable. Right now I'm going to focus laser target on this, though. All right, so the 8 queens problem, I did a wonderful video on it, I personally think, so you can go into your recursion videos, and you'll see, like, at the end, I have this recursive backtracking video over here. And I have write-ups of the chess homework and the Sudoku right over there. But I always like to do these in class because I just have so much fun with these problems. Okay. I got to use that on my chessboard, and I kind of solve it as a 4 queens problem. You can solve it as anything. So for those of you who don't know, the queen is the strongest piece in chess. It's worth 9 points, so it's the most valuable piece other than your king. And the reason for this is that the queen can move in any of the 4 directions that are cardinal, as well as any of the diagonals. So basically, if it's a straight line, the queen can move in that direction. Okay? That's what makes the queen so powerful. She can move any number of spaces until she runs into a piece. Very, very powerful piece. You only get one. And managing to capture your opponent's queen without getting yours captured in return is generally a signal that things have gone poorly for the opponent. The 8 queens problem asks the question, okay, given a chessboard, how can I put 8 queens on a chessboard such that none can capture each other? And if we go to our PDF, again, I was able to actually program this in LaTeX, and it just kind of formatted. This is actually not an image. This is actually embedded.
Someone took the time to put that in there. You realize this, right?
It's crazy. So anyway, so here's an example. Here are 8 queens on a chessboard. Chessboards are typically 8 by 8. You have it's an n. So chessboards are n by n, and the 8 queens puzzle says let's put n queens on this n by n board, such that none threaten each other. To threaten each other in chess, if a piece threatens another piece in chess, that means one piece is saying I can capture you to another piece. So in other words, in English, place 8 pieces on this chessboard such that none are in a single row, a single column, or diagonal. None share a column, row, or diagonal. So you can see that this queen on B7, on column B, row 7, there's no other queens on column B, no other queens on column 7, and then there's no other queens in that diagonal. If there was a queen here on C6, that would be violating this queen, and this queen, right? It would be violating a row, a column, and diagonal. All right, that's that problem. The next problem is the Knight's Tour, which basically the Knight is a very fun piece. It can jump over other pieces in chess. Other pieces, they kind of stop their movement as soon as they run into a piece. The Knight jumps in a L shape, okay, as noted by these 8 possible moves over here. The Knight's Tour basically has only one piece, and the idea here is I want to have this Knight visit every single square exactly once on the chessboard. Make sense? So no going on any other, and so you can do either of those problems. It's and your output basically should basically have each square being a number, saying okay, first here, then the 1 is where the Knight starts, 2 is the next place, 3 is the next place the Knight visits, 4 or 5, and so on and so forth. All right. These are both solved by representing the board as an 8x8 double integer array, right? Simple, pretty simple. In this case, in the queen's case, I would basically use a 1 to represent the presence of a queen and a 0 to say there's not a queen. You could also use strings or characters, it doesn't matter, right? So long as you can print it out in a reasonable manner and you can just visually check it. Okay, now how do you solve either of these problems? Well, the answer is recursion, obviously, but I give you this algorithm at the beginning for solving something involving a board with, or for solving a puzzle using a recursion, recursion with backtracking. Now, recursion with backtracking is essentially what you were doing with depth first search with in the maze puzzle. Basically, you continue keeping track of where you are on the stack until you need to back up. Okay, so if you need to, you can always refer back to that. But this is the way it works. It's a solve method. It's going to return true or false. That's very important. Okay? It's going to take in the board, whatever that board is. In other words, the puzzle you're trying to solve, and then your position. So the key to solving recursive puzzles like this is you always think locally. You got to think lazily. You think, gosh, this is a really big puzzle. I'm lazy. I'm going to try to solve a single step of it, and then I will recursively solve the rest of it. It's going to be some other sub-process's problem to solve the rest of the puzzle. So the position lets you know exactly where you are in this board, where you are trying to solve. It can be trying to solve a single square. It can also be, in the case of the 8 queens, as we'll see, trying to solve the entire column, which I'll get to in a second. So if the position is such that there's nothing left to solve, in other words, we are at an end condition, such as we are off the chessboard, or we've gotten to the 65th place. And position might be, again, can be 1 or more variables. Okay. But if we finish if basically the first thing, the position we should be able to check the position and let us know, hey, are we done with this? If so, true. Then, if that's not true, then we check for every possible choice we can make from this position. We ask ourselves, is this a valid choice? If it is, say, okay, this is the change I'm making to the puzzle. This is where I'm marking the board next. And then if solve board position +1 is equal to true. So I do a recursive call inside this if statement. This is the trickiest part of this. So basically I say, I'm going to try to solve the next position. And if I get a true back, I'm going to return true. Remember, we return true basically saying if we're done with the puzzle. So if my sub-process returns that we solved the puzzle, I'm going to tell whoever called me that we solved the puzzle. Make sense? Otherwise, if I get a false, well, that position was not going to lead me to a solution. So I erase my choice, or mark it that is a bad choice somehow. And then, but in this case, generally, we just unmark that choice. And if I go through all possible choices and I exhaust my basically exhaust my possibilities, like going through the maze, checking all directions and you can't go in any directions, then in that case, I'm at a dead end. So if necessary, I clear any choices I made, basically saying, hey, this is a dead end. And then I return false. Returning false is how we signal, hey, this is a dead end. Returning true says we finished the puzzle. So let's look at this from the 8 queens, from the perspective of the 8 queens. Now the 8 queens, we're going to take advantage of the fact that in this 8x8 chessboard, right, we can only put 1 queen per column, right? There can only ever be 1 queen per column. Yes? Because if there were multiple queens in a column, you'd have an issue. So in other words, we can change this problem, the subproblem to, hey, given a column, where in this column should I put the queen? Make sense? So if I have a queen here, then, and this is a 4x4, I would want to kind of check, can I put a queen here? No. Can I put a queen? I'll try, is this a safe place to put a queen? No. Is this a safe place to put a queen? Yes, it is. Watch the video for more details. And then I'll go on to the next one. I try to put a queen here, but can't, here, but can't, here, but can't, here, but can't. And so what I have to do in that case is backtrack. And then I try the next row. I'll take a look at how that works algorithmically. So I pass in the chessboard and what column I'm currently working on. If the column is such that there's nothing left to solve, in other words, if the column goes out of bounds, right? If I try to solve column I, for instance, right, or 8, column 8 rather, if it's 0, 1, 2, 3, 4, 5, right? If I try to solve column 8, then that means, hey, I'm done with the puzzle. Return true. Next, for each possible choice, so in other words, for each row in the column, I'm going to ask, is this a safe place to put the queen? If it is, I'm going to assume that's the answer and then try to solve the next column. That's what this means, right? Solve the board, position +1, column +1, to the next column. And if that returns true, great. Otherwise, so marking the board this choice, this means I basically say, hey, this square in the array, that gets set to 1 or Q or whatever. If I can do that, great. If that doesn't work, set it back to blank or 0 or whatever. If I go through all those choices and none of them worked, I'm just going to return false. The big thing about recursion is that it will seem to work like magic. It doesn't. It's actually just very elegant. But it seems to look like it shouldn't be that simple. If you get stuck on it, please just reach out to me. Sudoku is a bit easier to see, but I will mention this. Often, so I'm just going to mention this up front. The biggest issue I see with Sudoku is that students don't follow this format, and they don't actually make it a recursive puzzle, even though they do recursive calls. What do I mean like that? Often what I see is that I see a triple nested for loop over here, where students look for the next row and next column that is blank. So for every row, for every column in that row, check to see if that's a blank square, and then try to solve it. If you do that triple nested for loop, I'm going to tell you that's not going to work because there's some puzzles where that will fail on, or that will accidentally change squares that should not be changed. Instead, you always for solving the Sudoku problem, you want to pass in the board and then the current row and column you're trying to solve. So let's go ahead and actually try to look at a Sudoku puzzle. So what in the world is Sudoku anyway? A lot of students misspell it as Sodoku. It's Sudoku. It's a Japanese word, but of course, it's not the only puzzle that, being a number game, it's come up in other cultures, like here it is in France in the 1895s. The idea here is that you're given a puzzle that looks like this. In fact, we'll go to the New York Times in a minute because they have a Sudoku puzzle basically every day. And you're supposed to fill it out according to rules. And here's the completed puzzle. And the idea here is that the rules are you're given these black these squares with the numbers filled in black. And the way you solve it is you have to fill the grid such that no row, column, or 3x3 square has a repeated number. So this row has the numbers 1 through 9 exactly once. The column has the numbers 1 through 9 exactly once. And this 3x3 over here has the numbers 1 through 9 exactly once. And those 3x3s, as you can see, are denoted by thicker lines. Right? It's not any arbitrary 3x3 square. So let's look up Sudoku on the New York Times, and we're just going to go through this. Okay. let's go with an easy puzzle just for a second, because you can kind of, with easy, you can see how, we're going to first look at how a human would solve this, right? The way a human would solve this is they'd note, okay, we've got 1, 1, 1 here, there's a 1 here. Is there a way I can solve I can figure out a 1? Well, there's a 1 here and a 1 here. That means that we can, a 1 needs to go in this column. 1 can't go here, here. So 1 can either go here, here, or here. So you might mark that down. Generally with the easy puzzles, what you can do is you can kind of figure out, okay, 6, 6, aha, we've got a 6 here. And where else can I put a 6? Can I put a 6? We know a 6 has to go in this column over here, right? Because there's a 6 here and a 6 here, right? So it's a lot of using kind of logic to try to figure out, okay, where can I put these squares? Is there any other ones that we can see? Let's see, I'm just trying to show, let's see, 3, 3, not promising there, 5s. Here. Nothing that pops out, unfortunately.
One between 9 and 8.
One over here?
No, down, go down.
Ah,
Yeah,
yeah, you could, but is that the correct place for a 1?
it is.
All right, what's the logic behind that? So,
There is 2 rows, right? With ones.
right, right, there's a 2, oh, right, a 1 and a 1 over here. So the only place you can put the 1 is here.
Yeah.
Yeah, of course. Definitely need more coffee. All right, so what we've got over here is that we've got, and so you would kind of logic things like that. Your algorithm is not elegant. It is the result, it is a sledgehammer. It takes a sledgehammer to the entire idea of this puzzle. We start over here at the first blank square, and we ask ourselves, all right, does a 1 work here? Great, move to next square. Next square is I'm going to recursively solve the puzzle by going to the next square. This square is fine. It's a base case. I'm going to recursively solve, not base case, it's a easy recursive case. I'm going to solve the next square. This square says, gee, I can't solve the whole puzzle. I can try to solve my square. Can I put a 1 here? No. Can I put a 2 here? No. Can I put a 3 here? No. Can I put a 4 here? Sure, I'm going to move to the next square. 1, 2, okay. 1, no, 2, 3, 4, 5. 5, great. 1, 2, 3, 4, 5, 6, 7. And then it goes on. So can I put a 7 here? 1 here. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 4. And then it just keeps going on until, and then if I have to, with the easy puzzles, you don't necessarily often have to backtrack. Well, I'm wondering if we do. 3. It's only up to 9. 1, 2, 3.
Basically, we're brute forcing.
So that's the funny thing, though. Although there's a distinction here, because a brute force would imply that, this is perfect, actually. Brute force would imply that, notice that this does not work over here. There's no choice that works here. We have to backtrack. Brute force implies that we would also try all the combinations from this dead solution. In other words, we'd also try solving this and this and this, but here we detected the entire tree of problem that goes up to here is dead. It's unsolvable. So we are pruning it in advance by backtracking. Then we go 6, 7, 7, and then 9, 8, and so again, 8, 9, 3, 4, 5, 2, 3, 4. And then you just keep going forward until you get a number that works. See, we found something that works, and then we keep going forward. If we have to backtrack again, we backtrack again. And your computer is just going to do this really, really quickly. Technically, this is an NP-complete problem. NP-complete problems, by the way, are really nasty. NP-complete problems, simply put, non-deterministic polynomial, that's what it means. It means basically you can solve it in polynomial time. In other words, something that is you can solve it. Finding a solution takes this amount of time, n to the dth power. That's what polynomial means. So linear, quadratic, right? Linear time would be n to the 1th. Quadratic would be n squared, right? Those are all polynomials because they involve a polynomial. It's something with an exponent. Non-deterministic polynomial in layman's terms means it's going to take a polynomial time to solve if you're lucky and you choose correctly every single time. So generally speaking, that means that your runtime looks something around, instead looks like this. Where C is some constant and N is the polynomial and N suddenly becomes polynomial. Or it might be something like this. They're nasty. And they've got some amazing properties, which is that, like, for instance, if you can solve one NP complete problem, you can solve them all. This is something that should be covered in 3223. I've linked to a video in a playlist called Worth Watching. And so that is worthwhile if you want. But long story short, the reason why, even though it's one of those really nasty problems, the reason why it doesn't take too long is because actual implemented Sudoku is always this 9x9 board. On the other hand, though, if we were to generalize this puzzle, right, to basically an n-by-n Sudoku, then suddenly it becomes an n. Then that's where we see that NP complete come into play, and it becomes exponential. Another way to define NP complete problems is that it takes this amount of time. Sorry, I should say a property, not a definition. Is that it takes something along the lines of this amount of time to solve, but to verify if your problem is correct, it takes polynomial time. So in other words, hard to solve, relatively easy to check if it's correct, right? The solving process for checking for Sudoku is difficult, right? For a human, right? Solving this puzzle would be difficult, but if I were to hand you the puzzle, you'd be able to easily check to say, is this the correct solution by checking, are there any, any violations? Make sense? And basically the big question that NP complete kind of is probing at is there a better way to solve a puzzle than by just doing it? Some problems, like addition, you solve those by doing addition, and you check it by doing addition. The solving and checking is the same thing. It's very fascinating. So, in other words, the way this one works is, given a row and column, if you're out of bounds, what we do over here is that we say, hey, if you're out of bounds on the columns, go to the next row. If your rows are out of bounds, great, you're done. Then for every possible choice, that means the numbers 1 through 9. Well, there is actually, for Sudoku, there's something else we put in here, which is that if the square is already filled, because you're given a filled square, then just simply go to the next square. You should recursively solve the next square. So for every possible, because you have no choices. For every possible choice, though, in a blank square, what you do is you say, hey, if I can put something there, put that number there, and then try to solve the next square. And if that doesn't work, put the 0 back. Make sense? So that is how this works. It is actually rather similar. It will be rather similar. For both of these puzzles, what I suggest for the 8 queens is that the first thing you should do is code up an isValid function, right, before you solve this. Code up this isValid function for both of these, and don't finish it. Instead, what you do is just simply have it return true. In other words, treat every square as valid. Treat every choice as valid. Because what you want to do is you want to see get that recursion working first. The recursion is actually the easy part once you wrap your mind around it. And what that will mean is that for 8 queens is that if you correctly implement it with the isValid accepting everything, it will give you a solution that looks like this, where the queens are just across the top, because it looks at the first possible square, says that's a valid choice, and then goes, aha. But once you get that, you know your recursion's correct, which is awesome. And then you can say, okay, well, I want to make sure that they're not in the same rows, and then I want to make sure they're not in the same diagonals. Same thing for for Sudoku. If you do your Sudoku puzzle and basically set it to immediately be true, your problem is going to look like this. It's going to look like this, where basically you fill it up with ones. That's obviously incorrect, but if you have ones where the previous choices, where the choices are, and then you have all the rest of the numbers correctly filled out, the numbers that were given to you filled out still, then great, that means the recursion's working correctly. And once again, what you would look is like, okay, make sure it works for the rows, then the columns, then work on the 3x3s. The last piece of advice for the 8 queens problem is that I will give you one kind of piece of advice to make sure it's not overwhelming. Okay? The queen, as I mentioned, can move in 8 directions. So you might think, oh gosh, Professor Rosen, that means I have to make 8 checks. And the answer is no. First off, you can't, we're kind of already assuming you can't put a queen in the row and column, right? So it's all, in the same row. Same column. Which means because we're always taking a queen and kind of picking up and moving her in the same column, you never have to check if there's a queen directly above or below you. Second thing, we're moving right to left, left to right when we're solving this, right? When we're doing Sudoku, doing this, we're going to solve this column first, then this column, then this column, then this column. If we're going left to right, that means there's never going to be any queens to the right. Make sense? Because we're going left to right. The right is going to be our unsolved space. As a result, you don't have to check these directions either. So none of those directions. That leaves just these 3 directions to check. Now, the other piece of advice I will give you is that for each of these directions, you need a for loop. And that for loop does not need to be nested. Okay? This should be fairly easy to solve. But solving something like this will have you write a for loop you may not have had to write before. It will look something like this. For int, basically I, and you want to kind of start out with your row and column. And then you'll have, and then you'll have your condition, and then you'll have, and I'll solve that there, and then you'll have I++. And the key thing over here is that you typically write something like I is less than 8 or whatnot, right? What I am going to tell you here as my big hint is that this can be any Boolean expression you want. And I highly recommend making it a compound Boolean statement because that will make it a lot easier. Okay? Basically, use that, keep it like this. Set I equal to 0, I++, kind of like start expanding from the square, start searching from the square you're in and look outwards. This is what you're looking for. This is the key to solving that. Basically making a more complicated situation like this. If you're doing nested for loops to try to figure out if something is valid, you're having a bad time. All right. I've droned on for a half an hour. That's long enough.